Okay, thank you very much. Good morning or good afternoon, everybody. So for those who doesn't know me, my name is Denis Cornet, and I'm a crop physiologist from Cirad. And as Eglantine introduced, the goal of the presentation is to explain a bit how recent advances in deep learning offer new possibilities to better predict functional traits of RTB products. So my presentation will deal a bit with methodology, but very briefly, just in order to explain why we choose deep learning, to describe a little bit the network architecture, and to give some few explanation about a type of neural network called convolutional neural network. And after that, I will come to the main dish, I mean, the result we've got on different database, RTB database, of course, on composition and on functional traits or global quality, what we call good-bad protocol and good-bad genotypes. So first, why we choose to work with deep learning. Mainly when we looked at NIRS calibration, we thought this is only a problem of predictive model. So we need to develop the best predictive model. We are not really interested in explaining why or how it works. We just need a very good prediction. And this is what we are aiming to in this presentation, only prediction. The second point is that to realize this prediction, we have a huge amount of explanatory variables. Most of the time, we have more than 1,000 wavelengths. So meaning more than 1,000 explanatory variables. In deep learning, we call it features, but it is quite the same. So we have a huge number of explanatory variables. And because the reference measure associated with it is most of the time difficult to get or costly, we have nearly always a higher number of explanatory variables than samples. And finally, in most of the calculation behind the calibration, there is nonlinear relationship. So in such cases, machine learning nearly always outperforms traditional programming. Just to explain why, I show you how traditional programming is doing. We give some input data, a set of rules, and then the computer tries to find the way to get the best result as possible. But we constrain our research space by setting these rules. For PLS, there is a series of rules. If we choose a multivariate regression, there is other rules. If we choose a nonlinear last square regression, there is also a set of rules. So we constrain really the search space. And this is not really done for good reason. At the beginning, it was mostly done because computational capability of computer was not able to do better than that. So we fix this kind of rules. But nowadays, there is no problem to get higher computational capabilities. So with machine learning, we were able to change of paradigm. We replace the set of rules by the result. And in fact, we give to the computer the input data as in the same time than the result. And we ask the computer to look for the best set of rules for us. So we can look into a much wider research space, and you have a lot of more chance to get a better solution. And this search space includes all the nonlinear relationships, which are not able with classical PLS or very difficult to get with classical PLS or other classical methods. Still, to explain why deep learning is very interesting, most of the time in publication and for chemometrician, NIRS calibration means finding the best pretreatment combination. And for that, we have a lot of pretreatment types, R-transform, Savitsky-Golay, multi-scatter correction, D-trend derivatives, and so on. There is many of them. And we can combine them up to degree 6. So it means we can make 2 R-transform, followed by 1 Sav-Gol, followed by D-trend, and finally 2 derivatives. So there is a huge number of possibilities of pretreatment combination. And the way to find it, of course, there is some knowledge, but there is also a lot of empiric work. So it means we test it. If it's not working, we test another combination and so on. It's taking a lot of time. And after having found the best pretreatment, we apply a modeling strategy, whatever it is, PLS. And in PLS, there's so many PLS. There is a modified PLS with WinEasy. There is a local PLS, IPLS, and so on. So we have to find a modeling strategy. There is all the PLS. There is also the classical one, lasso, ridge, elastic net, random forest, non-linear last square regression, support vector machine, and an increasingly higher number of neural networks, convolution recurrence, long short-term memory, neural network, and so on. So there is a huge diversity to explore, to find the best solution. And publication deal with optimizing this solution for one analyte. In our opinion, we agree that the optimal combination of all this may differ between analytes and studies, but the way to find it could be generalized. So it means we can find one architecture that will always give a very good result. And this is what we've done. We hyperparameterize some neural network architecture to find the best architecture to always give very good results. And this is much more easy to do this type of pipeline with machine learning, because within the architecture, the way to find the solution, the set of rules can be still very vast, even if the architecture is fixed. So just to describe in few steps how the algorithm works. First, we split the data set. We can do it if the user or the owner of the data set give us the train and test data set, we don't have anything to do. But if it comes in one whole data set, we split it into calibration and validation data sets. The validation data set is set beside, and we don't touch it until we want to check if the results are performant or not. And to do this split, we use the canard zone algorithm, which offers the possibility to cover the spectra diversity in both the train and test set. So we ensure that we cover all the diversity, and that the validation data set is not with a too narrow diversity. After this calibration, this split between calibration and validation data set, we make some data augmentation using noises. So it means starting from one spectra, this is the black one on the graph, we create artificial spectra with specific deformation, specific noise. And this noise are studied to mimic the undesirable noise present in the common data set, meaning, for instance, effect of the room temperature. We don't want to analyze it, we don't control it. So we want the algorithm not to learn on it. So we introduce this type of noise to make the result more robust to experimental or product variability. For instance, granulosity, room temperature, and so on. And the other good point of this data augmentation is that it can balance the distribution of values, and this is very useful for classification. So we can have more or less the same number of samples for each class, and then we can find a better solution during the calibration. After this step of data augmentation, we made the step of feature augmentation. So it means we increase the number of explanatory variables. We are doing it by making some filter combination. We make a lot of combination between the classical filters. It is not obligatory, but we found that it makes the conversion faster. And also it allows us to explore a wider combinational space. Because compared to classical method, where only the best pretreatment combination is kept, we keep all the combination. So it means if we have 200 combination and 1,000 wavelengths, we come with 200,000 explanatory variables. So it increases a lot the possibility of combination between wavelength and transform wavelength. And after this 3 steps. We can do the neural network in itself with cross-validation in order to minimize the overfitting. Sorry. And just so the heart of this neural network is based on convolution. So it just spent one day to explain how it works. The idea is to choose a window size. So this is a rectangle on the graph. We can change the size. It depends of what we want. And on this window, we apply a filter, just like pretreatment do. But in place of forcing the pretreatment choice, we let the algorithm choose the best pretreatment. And it was proven 2 years ago that when the user finds the best pretreatment, the convolutional neural network is able to mimic it, to find it also. But is also able to find a better one when a better one is available. So for instance, in 2018, they show that the best pretreatment was the Savitsky golide, followed by a first derivative. Sorry. And if we look at after the convolutional layer, the profile of the spectra is quite the same. So it means it was able to find back the same filter as at the pretreatment. So we can come to the results. So we started with some YAM composition, so very easy part, we'd say. We look for dry matter, protein, starch, and sugar. This is a database from INRAE and Cirad, and we have 236 spectra. All these traits were easily predictable with traditional methods, meaning modified PLS with easy. Yet the algorithm we developed was still able to improve the relationship. So this is a PLS result, and this is a machine learning algorithm, and we can see that it still improved even if the performance is already very high. Of course, the improvement is smaller when the performance is already very high, but it still can improve it. Moreover, it is also possible to unblock some predictions that were not predictable before. For instance, amylose was not predictable in studies made by Vincent Lebeau in the Pacific, and it was not predictable with PLS. But we applied it on a database again from INRAE and Cirad, and we found very good results with a R squared of 88.88 and a very low root mean square error. So it's also possible to use this machine learning algorithm to unblock situation with RTB composition. Now, what we are interested in is not composition, but functional traits or global quality. And of course, this relies on very complex mechanisms behind, very complex properties, and it touches to many compositional traits. But I think NIRS is the right method to tackle this because we have full information with all the wavelengths investigate. So this is possible to investigate with NIRS, in my opinion. But the main problem is that functional traits suffer from major constraints linked to reference method. When we come to functional traits, the reference method, if available, is nearly always less reliable and very tedious to apply. So it results in very small and noisy data sets. So the first problem is not about the difficulty to predict functional traits, but it is the difficulty to make the reference measure and to deal with small and noisy data sets. So I will give 2 examples with YAM moldability and YAM texture attributes, and with cassava cooking time. And one last point is that sometimes there is even no reference measure, and this is where Pierre Dardenne gives the idea of looking to good and bad genotype based only on stakeholder knowledge. So that's Emmanuel Alamou have done. He provided me a database with 100 samples of good genotypes and 100 sample spectra of bad genotypes, and we try to predict good and bad genotypes. So the first result is still about this Guadeloupean database with 81 spectra. We look at springiness, hardness, and cohesiveness. with very bad result. No, we were waiting for that, but still it's still very difficult to predict these traits. So we tried with the machine learning algorithm, and we come to a better performance, but still I'm not confident with this type of result. So the idea was to say that maybe for some traits, mostly functional traits, breeders do not need a precise quantification or quantification of functional traits. Maybe just a threshold is enough to screen the breeding material. So the idea is to look at classification methods for which machine learning is even more powerful. And this classification will give an idea of, for instance, is the cooking time good or bad? Is the moldability good or bad, and so on. So this is what we have done on this texture or functional traits. We worked still on cohesiveness, moldability, springiness, hardness, and we try to differentiate cohesive and loose, moldable and not moldables, rigid and springy, hard and soft. And we get some very good results most of the time, except for hardness. We have a global accuracy of more than 80%. So it means 80% of time we classified right the sample, the spectrum. So this is a good screening tool for breeders if they want to tackle this question of texture or moldability. We've done the same on CIAT database with 142 spectra. For cooking time, we have a database of cooking times from 17 minutes up to 60 minutes. We impose a threshold of 25 minutes, and we get an accuracy of nearly 80% again. And if we move the threshold towards longer time, cooking time, we get an even better accuracy. So with binary classification, it's very important to have a good balance for the choice of the threshold between what we decide to classify and the distribution of the value, of the real value. We can talk about this a bit later. We tried also with Thierry to look at 3 different classes, so multi-class classification with 3 classes, less than 25 minutes, between 25 and 40 minutes, and higher than 40 minutes to cook. And we get to an accuracy of only 72%. So this is logical because with noisy data sets, samples near the threshold are hard to classify. So if we multiply the threshold, we multiply the uncertainty. Sorry. So we decrease the accuracy of the results. We also worked on the IITA database for good or bad yam genotype for pounding yam. Emmanuel provided 200 spectra, and we were able to classify them with an accuracy of 92%. So it was very efficient to classify good and bad pounding genotypes. So in conclusion, we can say that in every studies, CNN outperform traditional methods. So this is very good in terms of performance, but it is also very good in terms of genericity, because we don't need to think about pre-treatment, type of modeling, and so on. We just have to push the button and to see the result. So this is a very generic algorithm. There is no need to tune it too much. Most of all, it's open source tool, so it's all based on Python. So it means as soon as it will be published, it will be available to everyone. Another point is that CNN offer right now, already now, some very good high throughput prediction method for breeding, for breeders, at least for yam, good, bad classification or moldability or cassava cooking time. So in near future, we hope to be able to tackle other RTB product and product profile, either based on historical database or new trial. But the idea is also to be able to tackle banana, sweet potato, or cassava in different product profile. my advice, if we have to share database to test this type of study, is to keep as much noise as possible. So if there's 2 repetitions for 1 sample, don't average it. Keep the 2 repetitions, keep the 2 spectra. If you have 2 years, mix the 2 years. If you have 2 drying temperature in the oven, keep the 2. Because compared to PLS, which suffer from noise, CNN feed on it. So deep learning feed on this noise. And it allows the algorithm to only learn from the right variable and from the right features. The idea is to get a database of at least 100 spectra by classes. So as Emmanuel sent us, 100 of good and 100 of bad genotype was plenty enough to get a good calibration. Maybe we can also test this algorithm on other 1D signals, double compression profile from texturometer, audio spectra from texturometer also for milliness of reliability, water absorption profile, RVA, and so on. These all look like a spectra. It's always a profile evolving for spectra. For NIRS, it is depending on the wavelength. For water absorption, it's depending on time, but it is always a 1D signal. So it means in place of trying PCA and trying to know which variable will be the best to extract from the profile, we can let the algorithm do it for us. As long as we are only interested in prediction. With Lauriane Rouen and Grégory Beurier, which developed the algorithm with me, we want to improve the performance, and we have a significant improvement in front of us with model assembling. So we are working on it right now, and it will be, I think, the next step in improving the performance. We want also to test these artificial intelligence methods to improve the interoperability using variational autoencoder or generative adversarial network. These are very good tools, and this will maybe allow us to make some standardization, even unsupervised. So it means without getting samples from the 2 spectrometers. And finally, of course, we want to publish this algorithm so it will be available to everyone. So we are currently making some benchmarking about over 100 publications based on reference database, just to prove that it is possible to use it on small and big database from 60 to 20,000 samples on different spectrometer, different discipline, and different product, fuel, meat, mosquito, cartilage, and so on. Thank you very much.
Thank you very much, Denis, for this very precise and rich presentation on deep learning NIRS, which is for most of us, we have to admit, a quite obscure concept at first, but that's why also I gave you more time than it was first allocated, because we needed, I think, you to provide enough details for people who are not initiated to understand. So you have shown very well that how machine learning could be a very promising tool or method to bypass bottlenecks that food scientists are facing at lab level in the development of methods to disaggregate first and characterize and then measure the different components of quality. I've seen different questions in the chat bar, but please, people, if you have questions, you can directly raise your hand, and then we'll have a discussion with Denis. Yes, Denis?
Yes, I can already answer to Jan, who asked on the chat, how many samples do we need? And this is a very difficult question because it depends about the difficulty to predict the traits and the noisiness of the database. But what we have seen is that starting from 60 samples, we can already have good results. we also have seen that the advantage to use machine learning algorithm is reduced with small samples. So it's still more advantageous than traditional methods, but it is much more advantageous if we have much more samples.
And the second question from Jan was what VAE and GAN are.
Okay, so these are two artificial intelligence tools. The first is called variational autoencoder. So it is used to summarize the information, but without losing information. So it's a bit like PCA, but again, with a nonlinear method include and a much wider search space to summarize the information. The idea is to be able to extract from something, whatever it is, genotyping data or NIRS spectra, to reduce the quantity of information just to be able to keep the essential one. And normally you can find back the way to return to the original information with losing as less information as possible. So this is a summarizing tool. And the second one, the GAN, it's generative adversarial network. And it's a very special type of network, it's based on game theory. It is used to produce fake image or fake speech of people to say, to make Donald Trump saying something. We can use it or to change the face very realistically. This is the algorithm they used. For us, the idea is to be able to generate artificial spectra from one machine and sufficiently realist to mimic the second machine. So this will, we make a competition between one algorithm producing spectra and another one looking if it's real or not. And this will help us to I'm seeing the the comment of Jan. I think it's really easy to make the algorithm tell Donald Trump something clever, but I think nobody will trust this is a true story, of course.
Okay, thank you. We have two questions. First, Fabrice, please ask your question.
Yes, you can hear me?
Yes, very well.
Yes, thank you, Denis. Thank you so much for this very interesting presentation and the promising, all the promises of this kind of approach. You know that I'm confident that we will need this and we will use this. So my first question is about a specific aspect of the procedure. When you say that you do also features, explanatory variables, augmentations. I'm not sure I understood, because when you use a derivative or filters, you reduce the number of features, you don't augment. There is no augmentation, no? Hello?
Yes, but we keep both. We keep the original features, we keep the derivated feature, we keep the R transform feature, and we all put them in parallel. So
I would say clever. I would say clever. Another point is maybe we can think to combine. It's a very nice idea. I already used this in the past for audio. We can use audio spectra with your algorithm and do this, or texture profile or something like this. But what about combine NIRS and texture profile in the same data set and put it all together, even with chemistry value, if we have a chemistry value, and put all this together in the same data set?
So this will really not be a problem with machine learning, because you can feed.
Maybe it will be an advantage, no?
It will be an advantage. We will be more performant, but it will be also a less high throughput method because we need to collect more information. So the idea is
it depends, because once you have the models, you can predict after. So if it's better, but to mix texture and maybe it could be interesting to try to do this. I guess. Very, very interesting. Just a last point, how long it takes to do the calculation?
It depends of the size of the data set. It's starting from, you can't not do it on your personal computer. You need at least a graphic card, a GPU.
Mm-hmm. Yes, my question is because when we use local calibration, it's not deep learning, but it's a long time of calculation. Yes.
So it starts from few seconds to few days, depending of the size of the data set.
The beginning of the NIRS, at the beginning of the NIRS to do MPLS with 100 samples, it took one night. So it's a beginning. With the next generation of computer and quantic computer, it will be okay.
Yeah, and you know, for the hyperparametrization that Grégory Berrier have done to find the best architecture,
yes.
If I had to do it on my computer, it could take many centuries. So we had
to
send it to a super calculator based in Paris to be able to do the stuff, and it still took 1 week.
Yes.
So the building of the architecture is very, very difficult and slow, but once it is built, and this is the case, this is very easy to use.
Yes, of course. So the reason of Python.
This is all with Python, Keras, and TensorFlow. Yeah.
Yes. Thank you very much.
I see that Emmanuel is asking, and I have two questions in the chat, but maybe Emmanuel first.
Yeah, okay. Thank you very much, Denis. It seems most of my questions, Fabrice has covered it, but I still want to ask about the cost implications of, using machine learning, in replacing the traditional calibration model development. That is one. Then number two, I want to ask is how easy it is to integrate, for example, the model you have developed to be used by the breeders. That's one, and then to be used with the current NIRS equipment that we have. Thank you.
Okay, so you're right. To make the calibration, you need a good computer with GPU. So the cost is around 1,000 to 2,000. With the GPU, it will be 2,000 euro minimum. So this is to get the computer to be able to make the calibration. But you can also use online services, whatever Google or Amazon or all the big enterprise have this facilitation tools online. So you just access it freely in some situation, for instance, student and so on. And if not, you just pay for 1 month's use and things like that. It's not very expensive. So this is another solution. But once the calibration is done, you can give the model to the breeder, and all what he need is Python. Install on even a very old machine will be sufficient. So there is no equipment need for the prediction once the model is calibrated. Did I answer to your question?
Yeah, it's okay. Thank you very much. For now, not to waste time, we will discuss at our level, okay? Thanks.
Sure. Thank you also for the database, Manuel.
Please, just to complement, Emmanuel asked for how we can transfer the model to the instrument we use as routine instrument. It will be easier, or we will need we can imagine a kind of interface between a computer and instrument to do it in routine analysis, especially for phenotyping.
I'm not sure I understand the question, but the idea is only to collect spectra, and from the spectra you have the model. It's a small data file, and the prediction is instantaneous. So you only need the spectra, just like before.
Yes, but that was the question of Emmanuel, and it's a good question. When you use a spectra, most of the time you can put the calibration in the instrument, and you have in the same shot when you do the measurement, you have the prediction. So that means we will need to think a way to collect the spectra and to apply the algorithm.
Yes, it's not up to now. The development part of the tool is not done. So I'm sure once it will be published, private company will be very happy to include them in their instruments, because it is always better than PLS or what WinEasy is doing. Or so. So I'm sure this will not be a problem. The problem even will be to know how to do it without a commercial war.
Yes, yes.
I'm not worried about that.
Yes, yeah, I agree. Thank you.
Denis, we still have 5 minutes before we close, so I propose you address the comments, the 2 questions in the box. There was Gabi's one and Thierry's one.
Okay, so for Gabi, I didn't say that 60 sample will always be enough. I said we have done it with one database of 60 sample, and it was still more performant than PLS. But if the samples, even 1,000 sample is noisy and the trade very hard to predict, the performance will be bad. So the technique, the methods do not replace the quality of the database. The first thing is always to have a good quality database. And for this, I can't do anything. It's better with the machine learning because it's more resistant to noisy and to noisy data set, but it's not sufficient. It will not magically get result when it's not possible. So 60, we can start to try, but without promises. What I can promise is that most of the time it will do much better than PLS and classical calibration. Thierry, why noise is good for machine learning? Noise is always present for me in my understanding. I'm not a specialist, but with spectroscopy, noise is always present. Whatever it is, room temperature, humidity of the sample, oldness of the machine, whatever the cause, there is variability. The systematic reflex of traditional analysis is to remove as much as possible, even if we discard some sample, to get a very good and very precise prediction and calibration. In my opinion, it's not maybe the right way to do it, because variability will still be there with the prediction database. So we need to be able to tackle this variability. And the best way to tackle it is to tell the algorithm how to not learn on the noise. That's why machine learning are very strong. They learn that it is a noise, and they learn to set aside a part of the explanatory variable or combination of explanatory variable because they are linked to room temperature and so humidity and so on. And they learn to extract only the useful and stable information. And so to make them able to be more robust in this way, we keep as much initial noise as possible, but we also add some more noise, which produce artificial spectra. This is the work of Lauriane Rouen.
But then, if I can ask a complementary question, how does the machine learn, or how does it identify what is noise and what is not noise?
For instance, if we produce artificial noise, we have the initial spectra with, for instance, a cooking time of 17 minutes, and we applied some specific noise, dilatation, rotation, augmentation, change of baseline, and so on and so on. But it is still associated with the 17 minutes. So you have the algorithm has a diversity of spectra with a lot of noise, but with the same value. So he is obliged to look only for relevant variable and variable combination to predict the 17 minutes.
Okay.
There was another question from Elizabeth, if it can be applied or if it would work with both portable NIRS and tabletop and portable or handled NIRS.
Yes, whatever the size of the wavelength, whatever the size of the type of spectrometer, it is working. Yes, it's not it's not blocked by a specific type of spectrometers, but it is not made for standardization for now. It's for calibration on one tools and prediction with the same tools, with the same spectrometers. Standardization is another problem that we want to tackle with other solutions.
Okay, and we'll take one last question from Afola.
Okay, thank you, Denis, for the presentation. We want to ask, is there another testing phase that allows the model retrain itself with additional testing data?
Excuse me, I didn't get you.
Yeah, so is there a testing phase, where people load spectral data and the model you have developed will retrain itself to probably increase the accuracy in a way?
Okay, I get your point. So it's how to use it easily without getting bored by Python and so on. This is a very good question. I think the first step is to prove that it is efficient. We are on the way for it. And the second question we will have to ask ourselves is which type of tool do we want to use it? And this is another part for informaticians. This is really development part that I'm not competent for that. And this is a question we will need to ask ourselves in the next years. If we want to use this methods, what type of tools do we want? Do we want it to be associated with one instrument, but then you will have for sure copyright? For instance, if we sell it, not sell, but if we give it to FOSS, you will not find it on ASD, and so on and so on. So including it on the instrument interface, for me, is not a good solution because it is privatization. For me, the best solution would be to have an online tool linked with computer and GPU elsewhere to make the job for us. But I'm not the one who will answer this question. I think the user need to tell what they want, how they want it, and then we can think of the best solution.